Hey everyone, welcome back to Ueducate. Today we're going to break down one of the most important ideas in stats, the normal distribution, also known as bell curve. Once you understand the basic idea, I'll show you exactly how to work with it in Excel using two functions, normal distribution and normal inverse. By end of this video, you'll able to answer the question like what is the chance of getting the exact value, what value cuts off the top 10% of my data. Use nothing but simple Excel formula. Imagine a class of students take exam and most students score somewhere around the middle, close to the average, and fewer students score high and fewer score really low. And if you plotted every score on the graph, you would get a shape like this. This is the normal curve and this is the data, so x and this probability density, and then we plot a graph and we get the normal curve distribution and bell curve. So there are two numbers that describe this curve, which is the mean 100 and the standard deviation. This is how the spread out the values are. For example, we have let's say our class has a average exam score, which is the mean 100 and the standard deviation is 20. So here's something really useful. Every normal distribution which follows the empirical formula that is called 68, 95 and 99.7. 68 is that values fall within a one deviation, which is a 100 plus minus 20 between 80 to 120, and 95 is that values fall between the two standard deviation between 60 to 140, and 99.7% of values fall within a 3 standard deviation, which is 40 to 160. So this give you the exact gut check on any value, but to get exact numbers we'll turn to Excel. So I've got this data over here. In B1 cell we have a mean and in B2 cell we have standard deviation. If we want to know what is the probability of a student score exactly 92. 92 is just below the average and very close to the middle of the curve, and we will use the formula this is equal to normal distribution. Our what value we want, 92, B5, and B1 is our average value, B2 is standard deviation, and false because we just want exactly this number, and then we close the parenthesis and we get the data, which is 1.84%. Because we this is if we do the journal function, then we get the like if we is equal to normal distribution and then we have our exact number we want, and then we want our B1, we have our mean, B2 we have our standard deviation, that's the probability mass exact number which we want, close the parenthesis, this. But if I change the value to just numbers, we will get this number 0.011. and if we change if I want this number to look into the percentage, I will change into the percentage. Now the next question is, so this 92 is just below the average and fairly close to the middle of the curve, and then we calculate this by using the formula. So this gives us the, when we select the false, that gives you the probability of the single point, not a range. So this 1.84, that might sound tiny, but remember that 99.7% of all the score spread across the range 40 to 160. A single exact score will always have a small probability. The fact that 92 is so close to the average give us the 1.84%. Actually tell us it's one of the more likely the individual values. So our next question is, if we want the probability of a range, what's the probability of student who get the score 92 or more? That is the cumulative probability. This time we are not looking at one point, so we want a whole range. We still use the formula normal distribution. Now we set our last argument to the true. So this is our formula is equal to normal distribution. Our b5 is 92 or more, and then our mean and the standard deviation. This time we use the true, and then we get this 34.46. Now does that make sense? 92 is below the average, right? 92 is below the average, and on a bell curve half of the value sits above the average and half of the value sits below the average. If the 92 is below average, so more than half of the students should score 92 or higher, right? So this is the common mistake people make with this function. So let's clear this up. If we want 92 and more, so what we'll do in here, 1 minus normal distribution, our number 92, mean and standard deviation and true, close the parenthesis. Then what we have is 92 or more when we subtract from 1, because normal distribution with the true doesn't give you 92 or more, it gives you 92 or less. It's calculating everything left of the 92 on the curve. So that 34.46%, that actually probability of scoring 92 or less, right? So to flip that, to get the number 92 or more, we will subtract our result from 1. We will get 65.54%. That makes much more sense, since 92 is below average. The majority of the students, about 65.54%, score 92 or higher. So how to remember this? Normal distribution, the true, this value or less, then we get our, if we want value less than or equal to, then we want this true formula, and if we want more, then subtract from the 1. Now next is the so far we've started with the value and found a probability, but what if we want to go to another direction? Start with the probability, right? Start with the probability and find the value. That's then we which formula will we use? We use normal inverse, the inverse of the normal distribution. So what does score do? Bottom of a 33% of the student fall below. So 33% of the students fall below. What is the number? Is equal to normal inverse B11, 33% of the students fall below this number, and then our mean and standard deviation, then we get 91.2. like this. About 33% of students scored below 91.2, and the remaining 67 scored 91.2 or higher. Now let's try trigger 1. What score do top 90% of the students score above? 90% of this of the students score above, not less, above. So this is the same trap as before. If we just type 90% in normal inverse formula, give us the value below, which is 90% of score fall, not above. So again, we'll subtract. If we use, like, we just use the same formula like this one, right? If we want use is equal to normal inverse, and our number is b, oh, 90%, or should we say b13, b1 is b1 and b2, then we have this much of value, which is wrong, and we get this number, and this is the scores that fall, not above. So like this, it's nowhere like 90% of the value. It's because before fall, more student, if this is the value, that makes sense. On here, like 90% of the students get 90 and above this score 90%. But if the value is this one on here, that is fall, this is less than 90%. It's not 90%, because if we see on the graph, it's our this value showing up here, which is towards left side of the curve. So most of the values which falls below this range, not above this range. But when we calculate 1 minus, so our value sits there, and left of the most of 90% of the value sits here, that is above. When we get this point, 90% of the students scored above 4.37, which makes sense. That covers the big bulge in middle of the curve plus everything right of it. But if we don't minus and subtract this, so everything is to left of it, right? So we will use the formula 1 minus. So let's recap. Normal distribution describe data clustering around the mean with spread defined by standard deviation. There is empirical formula rule 68, 95, 99.7 rule that quickly estimates how values spread out. And if we want exact value, normal distribution, the value, and mean, standard deviation, and false. And if we want probability, the number or less, then we use the same formula, but at the last argument change to the false to true. But if we want more, then like number and then more than that number, we subtract from the -1. So if we want the value below what that probability of data falls, and then we use the formula normal inverse. So that's it. Normal distribution, normal inverse are incredibly handy anytime your data follows a bell curve, test scores, product measurement, delivery times, heights, weights. So if this helped, smash the like button, subscribe to Ueducate for more practical, excellent data analysis tutorials. Drop a comment if there's a topic you would like to cover next. Thanks for watching. See you in the next one.